All right, so what do you do?
I'm doing a PhD here at NUS, so in Singapore. Currently doing my fourth year at Operations Research and Analytics.
Before, what and where did you study?
So I did my bachelor's and master's back home in Sweden. So there's this university called Umeå, which is quite far north in Sweden. My main degree was engineering physics,
Okay.
but then I also got some interest in statistics and data science towards the end of my education. So then I also did an extra degree in statistics.
I went through your profile and I noticed that it's very versatile. You did a lot of projects on very different topics. I just gonna read it out. Robot to robot interactions using causal interference, black box optimization in high dimensions with applications to pre-hospital care, and my favorite, evaluating machine learning models for predicting glioma from single nucleotide polymorphism data.
Yeah.
And finally, data management within asset pricing research. So tell me, how did you manage to dive into so many different topics?
I would say, even though they might seem very different, I think the main kind of common factor between them is machine learning or data science. So even though the projects themselves are very different, the common denominator is some kind of machine learning data science. The Glioma project was quite purely a machine learning. So basically, we just got a lot of data from the hospital close to my university, and then they asked us to try to predict, oh, is this person gonna have glioma or no?
Okay.
Yeah. So I think a lot of these also like random encounters. Like you just talk with a professor and then they say, oh, I have this project.
Yes.
And then they say, oh, it sounds interesting, even though I have no clue what it's actually is going to be about. But then as you work on it, you get more of a full picture of what this.
Do you design your machine learning models for each application? Do you put any inductive bias into the model architecture considering the application, the problem you are trying to solve?
For these projects, like the bachelor thesis wasn't that advanced, I would say. We had mostly the pre-processing
Yes.
was kind of specific to the application.
Yes.
But the machine learning models themselves, we didn't do too much specific to that problem.
So among these projects, what was the most difficult for you and what was the most interesting project for you?
The most difficult, I think, in terms of getting good predictions, I would say the glioma one, because the data for that one was very, very noisy. So one of the characteristics with the nucleotide data is that it's very noisy,
Okay.
which means it's very hard to do good inference from that data. And I think that was quite a challenge to try to overcome.
Are you saying that the target variable was not too clean?
I would say the data itself, like not the target, but the explanatory features weren't that good. I think that was my probably the most hard problem. But then I would say the most interesting one was the last one. So my master thesis, which was the ambulance care project, where we looked at optimizers, trying to figure out how to do placements for ambulances. And finally, I think we got quite okay results for that one.
Okay.
Which made it very motivating that you can actually use machine learning to do real world stuff that's actually useful.
How did the data look like?
So for that one, we got the data from the university hospital, and basically it's just zero, ones, and twos.
Okay.
It's called single nucleotides. So either it's 0, 1, or 2,
Okay.
which is basically like the genetic information. And that's all the data that we have. So basically trying to use the genome to predict. What you essentially want to do is find cancer markers. Actually, when we did the project, they didn't have that many cancer markers. So the idea was that we might find some new ones that might be useful for prediction.
All right. So after that, you moved to Singapore. So tell me more about your lab.
So currently I'm working with this professor from Institute of Math. We don't really have a lab in the common sense, so I'm working directly with the professor. Then my program is the Institute of Analytics and Operations Research, which is a separate institute from the math department. So let's dive into the topic you are researching right now. So can you tell me a little bit more about your main research area? So my main research would be numerical optimization, and more specifically, when you want to do some kind of stochastic gradient descent on data that's not IID. So in my case, we're looking mainly at the autocorrelated data, which kind of breaks down one of the main assumptions of HGD, which is that the data is going to be independent. They were looking at methods to overcome this.
Is it somehow related to time series forecasting models?
Yeah. So basically, if you say that you have a time series data stream and then you want to do something where you require optimization on that one, then you usually run into troubles.
What variables are you trying to optimize?
So the variables that we usually want to optimize is that we want to find some kind of rate. So say that you want to do linear regression, which is like the simplest case, then you just want to find the slope. So basically that's the goal target variable that we want to find.
Yeah.
So then to do the optimization, of course, then you just put up some kind of loss function like MSE.
What is greater challenge, data or compute?
I think compute. I think especially nowadays, I feel data is very available. So then I feel compute might be the bigger issue.
In your specific domain?
In my domain, compute. What I'm doing, like my research project now, I think compute definitely is the bigger problem.
What are the sizes of the models trying to fit?
So basically, the model itself is very small because it's just like a linear regression. So the compute is mainly a challenge because I kind of want to iterate it on a lot of data. So then it's a bit slow getting through. And especially since we have some prefactors that take some time calculating. If you want to, you could synthetically construct some data. So then you can get as much data as you want. But because of the computing time, that's usually where it kind of lags behind. And I usually see it's correlating to how much you compute, how good the parameters become. And then, of course, the longer you run, the better.
I'm going to ask you for the papers you're referring to.
So the main method is stochastic gradient descent. And the main part about stochastic gradient descent is that it assumes population expectation is going to be the same. But the problem is if you have some kind of autocorrelation, if you just take the conditional expectation, it's not going to be the same as the population one. So you get this discrepancy. But of course, you want it to be corresponding to the population expectation. So what you then need to do is that you usually have to make some prefactor, or you have to modify the stochastic gradient method to get the conditional expectation to be equal to the population. So that's the research that we're doing currently, to just find this prefactor and then also show in theory and in experiments that it can actually help it being reduced to the population expectation. And that will in turn improve the parameter estimation that you get. So that's the whole idea that we're trying to explore.
You're doing the descent over one example instead of a batch, meaning that your gradient effectively becomes too noisy. Isn't it a problem?
Yeah, it is a problem, and you would get help by the batch, but the problem is if you have the correlation. So even over a batch, like it's not gonna be the same always. And the thing that we are trying to do, which is having this prefactor, which always depends on the data point just before. Maybe you could use some kind of batch mean, but currently what we're doing is not really applicable because you can only use the previous time point. And then if you take a whole batch, it's no straightforward way to apply the prefactor to the whole batch instead of one sample at a time.
This notion of a prefactor is not that common. Could you maybe clarify what that is?
Basically, when I talk about a prefactor, I say what you multiply before you take the gradient. So usually when you do stochastic gradient descent, you have some parameter equals the old value minus some step size times a gradient. So when I talk about the prefactor, is what you put in front of the gradient.
Kind of adjustable learning rate?
Yeah. Yes.
Oh, yeah. I mean, if you're the guest, so you need to be more comfortable.
I'm very comfortable here. Like, I'm not sure if it looks too comfortable, like if I'm just leaning back.
No. This is the idea. Okay, imagine that you have hundreds of thousands of H100s. What experiment would you run?
Or for that one, I would probably do Bitcoin mining.
I had a similar answer.